This tutorial shows you how to perform an analysis of molecular variance, also known as AMOVA, using the program Arlequin. This assumes you are using Ubuntu Linux version 20.04 as your operating system. If you do not have Linux, you can emulate it on your Windows or Mac computer for free. See the show notes for details. In fact, I am emulating Linux right now on my Mac computer using VirtualBox. Speaking of which, I have a VirtualBox virtual machine pre-configured with the software I will show you today, as well as other population genetics and ecological niche modeling software. See the show notes below for step-by-step instructions to download and hook up this virtual machine within your Windows or Mac computer. This tutorial assumes you have Wine installed on your machine, more on that later, and that you have downloaded and extracted the Windows, yes, the Windows version of Arlequin. That's the one on his website called WINARL35. See the show notes for more information. I like the Windows version because it has a simple graphical front end. You will find all of this software pre-configured on the virtual machine that I referenced earlier. First, open a web browser and navigate to my website, joshbanta.com. Click on Tutorials and scroll down until you see How to Do an Analysis of Molecular Variance using Arlequin. Click on File Needed for Tutorial. Wait while everything on this page loads. Click the Download button and select Direct Download from the drop-down menu. A quick word about this file. We created this file using another of my tutorials on my website called How to Make an Arlequin File from a FASTA file. See my website under Tutorials if you're interested in how we made this file. Once it is finished downloading, you can close your web browser. Now let's find the file. Click on File Explorer. If you're using my virtual machine, you'll have it pinned to favorites. Otherwise, you can search for it here. Navigate to your Downloads folder. Take the file that we just downloaded, output.arp, drag it to your desktop. Now navigate to your desktop. To be tidy, we're going to put this file in a folder on our desktop called Arlequin. To do that, select New Folder from the drop-down menu under Desktop. Name the new folder Arlequin and click on Create. Take the file output.arp and drag it into the Arlequin folder. Let's look at that file. Double-click on the Arlequin folder. Now double-click on that file output.arp. This file in Arlequin format contains the genetic sequence data for each of our individuals. The names of each of our individuals are here, and then the genetic sequence data follows here and below because it's diploid. There's our next individual, here and here. The data is organized so that the individuals are in different populations. The populations that the individuals belong to were specified in the earlier tutorial when we created this file. In summary, the file that you downloaded just now has the individuals, their genetic data, and the populations that they belong to. And if we click on Desktop, the folder that file is in, called Arlequin, is the folder where we're going to be saving our results as well. Now let's run Arlequin. Open up Terminal. Pin to the favorites here, or you can search for it down below. We have to find the folder where the Arlequin program is located. Not the Arlequin data file, but the Arlequin program. CD space. And then click on File Explorer again. If you already have it open, you could also just click on the File Explorer window. If you're using My Virtual Machine, navigate to the home directory, scroll up to the bin folder, double-click on bin, and then scroll down. The name of the folder is WinARL35. Take that folder and drag it into your terminal window. So now in our terminal window it says cd space quote and the path to the folder that contains Arlequin. Press enter. Type the following and I will explain. Wine space win arl35.exe. Punctuation matters. It's a capital W, lowercase I, N, capital A, lowercase r, L, 35.exe. Wine is a special piece of software that lets us run Windows programs in our Linux machine. Arlequin has a Linux version, but I prefer the Windows version because the Linux version is all based upon a command prompt, whereas the Windows version has a friendly Windows-based user interface. So press enter to load Arlequin. Now we will open up that project file. Click on Open Project. From the drop-down menu at the top, navigate back to our home directory. Double-click on Sample, which is the username. If the username of your Linux machine is something else, so if your name was John Smith and you called your user directory John Smith, that's what this would be called. Double-click on it. Double-click on the desktop. Double-click on the Arlequin folder on our desktop. And here's the file with our data in it, output.arp. Select it and click Open. If your screen looks like this, it was imported correctly. You should have a list of populations over here. It says samples, but actually this corresponds to populations. A couple of other notes. This tutorial assumes you are using diploid data. If you had had haploid data, you would have converted it differently as part of the previous tutorial. When you open your project, Arlequin just recognizes the data as haploid or diploid. You don't get to choose. So if you would have had haploid data, you would have converted it differently, and Arlequin would have recognized it as haploid data. But we have diploid data. Next point. My tutorial assumes the gametic phase of your data, of this diploid data, is unknown. I think that is better because we will be doing a locus by locus AMOVA, which I believe is superior to the other methods. If you were using haploid data, you wouldn't have to worry about the phase of your data, so that would not be an issue. But just so you know, it is possible to have your diploid genotype data be what's called phased, where the gametic phase of the data is known. But I have it imported as unknown. Again, that's something you can't change. That's something that's set that way based upon the way that we converted the file in the previous tutorial. But I think that's the right way to go. Let's run the analysis. We need to tweak some of the settings. Click on the Settings tab and click on AMOVA. Choose the locus by locus AMOVA. Keep the other one unchecked. From the first drop-down menu that you see here where it says Use Conventional F Statistics, choose instead Compute Distance Matrix. And then keep the second choice as Pairwise Difference. Select the box that says Print Distance Matrix. There's some other useful data we can get out of this analysis. If we click on the selection from the menu tree that says Population Comparisons, and we select Compute Pairwise FST. Do not check any of these boxes. You can keep these boxes the same, although you could increase the number of permutations if you like. You could lower the significance level if you like. Keep this as Compute Distance Matrix. Keep this as Pairwise Difference. Now we are ready to run the AMOVA. Press the Start button from the menu at the top. For this example, it runs very fast. In your example, it may take longer to run. That screen that you saw pop up, it would have stayed up and you would have seen more lines being written to it if, in fact, your AMOVA was going to take longer. We're done with Arlequin. We can close it. Let's look at the results. Open up File Explorer, navigate to the desktop, navigate to your Arlequin folder where we're storing our results. Arlequin always puts the results in a folder that has the same name as your data file with the file extension .res, meaning results. So when you see this new folder in your Arlequin folder, this is where the results are. Double click on it. And this file here that's .xml is the one that we want. But we don't want to double click on it because it will not open in a way that we can read the data. What you want to do is right click on it if you are on a Windows machine or if you have a Windows style mouse. Or if you're on a Mac laptop, push down on your trackpad with 2 fingers. From the drop down menu, select Open with Other Application. We don't want to use a web browser to open it. So we click on View All Applications. Then select Text Editor. If it's still not showing up, you could search for it. Select Text Editor and then click the Select button. And here's our results. Let me show you the most germane results that you'll be most interested in. Here we are. Line 391, we have our AMOVA table. It lists the source of variation, sums of squares, variance components, and the percentage variation. This is a standard table to report in analyses, master's and dissertation theses, and publications. This shows how much of the molecular diversity among your individuals is found among populations versus within populations. In other words, are your populations genetically different from one another or not? The more genetically different your populations are from one another, the higher the percentage of variation. These two numbers here will sum to 100%. So the more genetically different your two populations are from one another, the less genetically different individuals within each population are, relatively speaking. So the question is there more molecular diversity within populations or among populations? So there's your AMOVA table. Scroll down further, and you will find some p-values. This is the p-value that we're interested in right here. This is the p-value corresponding to FST. I'll have more to say on that in a moment. A p-value that's below 0.05 means that the FST is significant. If we scroll back up to our AMOVA table, this line of our AMOVA table corresponds to FST. So you could add another column if you were publishing this table. You could add another column that says p-value, and you'd report the p-value right here. Because the p-value is less than 0.05, FST is significant. What that means is that populations are significantly genetically different from one another. Now, the magnitude of how different the populations are from one another is determined by the relative percent variation among populations versus within populations. But the fact that the p-value was less than 0.05 tells us that there is a significant amount of differentiation among populations in terms of their DNA sequences. You can tell which population an individual came from with relative certainty based upon its DNA sequence. That's what a significant p-value means for FST. One more thing to note. Even though the populations in this example significantly genetically differ from one another, even though you can tell apart which population individuals came from based upon their DNA sequences, there tends to be a certain sort of genetic sequence, a DNA sequence for individuals from one population over here. There tends to be another distinct DNA sequence for individuals from this population over there, and so on. Even though we know that based upon the p-value, there's a problem. It may be that there's only two populations that are genetically distinct from one another, and all the rest of the populations, individuals within those populations, all have DNA sequences that are very similar to one another. It could just be one population that is genetically very different from all of the other populations, and that could be the reason that you're getting a significant p-value. So you may wonder, which populations in my study are genetically different from which other populations? And which populations in my study are genetically similar to which other populations? That's information you can't get out of this analysis here, the AMOVA table, but we do have that information in our results because we asked for pairwise FST values. So we do have that information in here. This is the part of the information here. This is the other part here, but it's not in a user-friendly format. I have another tutorial that you can find referenced in the show notes below and on my website that can show you how to, in a user-friendly way, look at the pairwise FST values so that you can compare individual populations to one another to find out which individual populations are genetically diverged from one another. In other words, which populations can you tell them apart based upon their DNA sequence, and which populations are not genetically diverged from one another. In other words, which populations you can't tell whether the individual came from this population or that population because they've all got the same sequence. For that, you're going to need to see the next tutorial.